University of Maryland, I'll be talking to you about using computation graphs to explain non-determinism to students. This is joint work with Professor Morazán from Seton University. Traditionally, formal languages and automata theory courses teach students by having them use pencil and paper. Now, if students have to work with complex Turing machines, such as this one, it can become quite complicated for them to draw this out, and then even more complicated for professors to then decipher that drawing. But not anymore. We introduce FSM. FSM stands for Functional State Machines. It's a domain-specific language embedded in Racket, and it was built for the Automata Theory classroom. In FSM, students are able to first design, then implement, and finally test their machines before attempting to write these specific proofs. Now, the idea is that if the design is correct and if the machine's implemented and tested, which is the fun part of it all, then this proof should be rather straightforward. Additionally, we have integrated a bunch of visualization tools. For example, SMGraph is an observer that returns the transition diagram. For example, this is a Turing machine. And it just really lets the student visualize the machine that they built. Now, one of the nicest features of FSM is that non-determinism is already built into the language, which means it should be easy for students to use, right? Well, wrong, because as it turns out, non-determinism in itself is still quite a difficult concept to grasp. Students need help understanding that there can be multiple computations on the same input word, and some of these computations might not even consume the entire input. In FSM, students are able to work with non-deterministic machines, such as nondeterministic finite-state automata, pushdown automata, or Turing machines. Then they are able to give an input word to the machine, and if that input word is accepted, FSM generates a computation trace for the student. There's even a dynamic visualization tool that literally lets the student step through the computation step by step, forwards, backwards, and it really helps the student understand why this word has been accepted. However, if a word is rejected, no trace is generated. And FSM makes that choice, and we'll see why. Essentially, it would be more confusing to the student than it would help them to trace every computation exhaustively. But that leaves the student with no debugging tool, no help to understand non-determinism whatsoever, which is why we came up with computation graphs. They are the only FSM tool that capture non-deterministic behavior for rejected words. But before showing you the graph, I'll walk you through some background, which really explains why we made the design choices that we did. Essentially, there are two ways to visualize computations, either as part of a computation graph or as part of a computation tree. We'll start with computation trees. On the left is an NDFA. Q1 is the start state, Q3 is the final state, epsilon denotes an empty transition. On the right is the computation tree for that NDFA on the input word BB. A computation tree traces every path exhaustively, starting from the starting state. Sorry. Nodes denote configurations. For an NDFA, that is the state that the machine is currently in, and the unconsumed input, the input still left to consume. Now, we found that students struggle with computation trees for three reasons. One, they grow large very quickly. Two, students are tempted to look for differences between configurations simply because they occur in different parts of the tree. For instance, this node Q3 and this node Q3, they both denote the configuration Q3b, the same configuration, which is not immediately obvious for students because it's in different parts of the tree. And finally, for PDAs and Turing machines that may only semi-decide a language, meaning there could be infinite computations, a branch in this tree would also have to grow on infinitely. One such system that sort of generates exhaustive traces, just like computation trees, is JFLab. In JFLab, the user is able to build a machine, give it an input word, and generate a trace. In this case, we have an NDFA, the input word of 7 A's, and down here is the beginning of a trace after 6 steps. Now, if the user wanted to step through the entire input word until it's accepted, that would take them 14 steps, and the trace would look like this. And that's only the beginning. You can scroll down. That's only half of the trace, and the input word is only 7 A's. It's not that long. And that just doesn't help the student understand nondeterminism, which is precisely why FSM chooses not to provide a trace for rejected words. So that was computation trees. The other way to visualize computations is as part of the computation graph, which is what Gedayu does. This is where we took this NDFA from. We have the same NDFA, but now we generate a computation graph on the same input, BB. Now, a computation graph still traces every path. Nodes still denote configurations, but now computations may have shared nodes, which means that one configuration has its own node, essentially. So, for instance, observe that node Q3 occurs 3 times in this graph, but it denotes 3 different configurations. This denotes configuration Q3 empty, because both B's have been consumed. If the machine takes this path, it will read 2 B's and end in Q3. The unconsumed input is empty. Q3 is the final state. This is an accepting configuration. This node denotes Q3B because 1 B has been consumed. It happens if the machine takes this path. Or the machine could also transition from here to here on empty, which is this node, configuration Q3BB. And we observed that students prefer computation graphs to computation trees, but they still struggle with this because Q3 still occurs 3 times, and this graph doesn't really look anything like the original transition diagram that they associate with the machine. FSM takes a different approach. Essentially, a high-level idea was that we wanted our graphs to look something like this. The main difference is that FSM computation graph nodes do not denote configurations, they denote states, which is the same in the transition diagram. Nodes denote states. And the result is that the computation graph is merely a subgraph of the transition diagram, which makes it really easy for students to associate one with the other. So now, before looking at the graphs, I'll give you a brief introduction to FSM and how to implement these machines. The student would use one of the constructors, make NDFA, make NDPDA, or make TM. They all take as input a list of states, an alphabet, a start state, a list of final states, a transition relation. Additionally, PDAs also take as input a stack alphabet, and Turing machines may take an optional argument, which is an accept state in the list of final states. If that's provided, it means that the Turing machine is a language recognizer. Now, for example, let's say that the student wanted to implement an NDFA for the language AB star or BA star. They would use the constructor make NDFA and give it the inputs: list of states, alphabet, a start state. In a transition diagram in FSM, that's denoted as a green circle. A list of final states. In FSM, these are double circles. And a transition relation. Each transition for an NDFA consists of 3 parts: the source state, the red element, and the destination state. Epsilon denotes empty. For example, DMTS is the solid arrow DMTS. Then the student is able to test this machine. For instance, the empty word, AB or BABA, are all in the language. These are all accepted. BAB and A are not in the language. They are rejected. Right. The student is also able to generate this transition diagram. Essentially, if the machine transitions into the top loop, it is able to read an arbitrary number of BAs. If it transitions into the bottom loop, it is able to read an arbitrary number of ABs. All right, now that works, that's great. But let's say that the student wanted to extend this language with the word ABA. They write this test, they want ABA to be accepted, but it's not. This test bombs. And now there's no tool, no trace that's being generated, nothing that helps the student understand why this word has been rejected. Which brings us to the computation graphs. The goal of a computation graph is to visually demonstrate why a non-deterministic machine either accepts or rejects a certain input word. Now, accepted words are easy. All that's necessary is to show that there's one computation that reaches any of the final states. But rejected words are more complicated because the graph has to somehow capture that all of the computations don't reach any of the final states, and it has to capture why they don't. We use colored state distinction to be able to trace the transition diagram, and we also have color blindness options. For NDFAs, the colors are black and crimson outline. Essentially, black is just a state that's traversed on any computation. Crimson means that at least one computation holds in this state. For PDAs and Turing machines, it's a bit more complicated. The issue with those is that they may only semi-decide a language, which means that there could be infinite computations. Now, we were thinking about how we wanted to handle that, and we decided to implement a cutoff threshold. The idea was that in a classroom setting, students are never going to work with excessively long input words. So if there's hundreds of steps in a computation, then it's highly likely an infinite computation. Now, if the student ever wants to work with long input words, they are able to provide an optional argument that can either raise or even lower the threshold. If there is a cutoff, the state in which it occurs is being highlighted in gold. If there is gold and crimson highlighting, it's at least two different computations. One is being cut off, the other one halts. It's never the same at the same time. All right, so this is all we need to know. Now we can look at the graphs. We'll start with an accepting graph. And this is what it looks like. On the left is the transition diagram for our example machine. The language is AB star or BA star. On the right is the computation graph for that machine on the input word AB. Now we use Graphis to generate this appealing layout. Now before even looking into the machine, the student immediately sees that the only crimson state is a double circle. This is an accepted word. There's also a message that also clarifies that. Now, for accepted words, we trim everything that's not used because this one computation is all that's necessary to prove that this is an accepted word. And it lets the student focus on only a subpart of the machine. Now, rejected words is when it really becomes interesting. Let's say instead of AB, we give it the input ABA. The graph would look like this. Now, there's a lot of things happening here, but before even looking at any of that, the student immediately sees that none of the crimson states are final states. This word is rejected, and there's a message clarifying that. Now the student can go into the graph and examine why this word has been rejected. And essentially, there's two reasons why a word could be rejected. The first one is that the entire input has been consumed, but the machine halted in a state that is not a final state. And this is what happens when a machine state is highlighted in crimson, such as A or B. Essentially, if the machine transitions to S, reads an A, reads nothing, reads a B, and reads another A, then it holds an A, which is why A here is crimson. On a different computation, it could also non-deterministically transition to B on empty, which is why B is highlighted in crimson. So now the student knows that here the entire input word has been consumed, but these states are not final states, so these are rejected computations. But there's a different reason for why a word could be rejected, and that's that not the entire input has been consumed. The way we simulate that in the graphs are these dashed edges and a dead state. These edges in the dead state are not actually part of the transition relation of the machine. They are only part of the graph to show that there are some transitions missing. For example, if the machine transitions to the top loop into R, here it needs to read an A, but there's no A transition. So the graph creates this dashed edge on an A, and then the rest of the input B and A is being consumed into the dead state. Similarly, in A, there's no B transition, and in D, there's no A transition. So now the student knows that if they do want this word to be a part of the language, they either have to make A or B a final state, or they have to add transitions to A, R, or D. Of course, if they do that, that will change the language, and they need to retest and potentially redesign. So those were our graphs. Now, we wanted to know if students actually use them, and if they do help them with nondeterminism. That is why we conducted an anonymous study at University of Lisbon. It was a class of 17 students, 9 female, 8 male, and they used our tools. They answered 5 questions about computation graphs on a Likert scale. Essentially, they were asked to which extent they agree with a statement. 1 out of 5 means they strongly disagree. 5 out of 5 means they strongly agree with a statement. And these are the questions and the results. The first question asked overall how useful are these computation graphs? Do you use them? Do they help you with nondeterminism? The second question asked if the graphs help you understand that there can be multiple computations on a word and how they behave. The third question is asked about the dead state. Is that useful? Is the cutoff threshold useful? And finally, is the coloring scheme clear? The results are displayed at the bottom. The x-axis is the Likert scale. 1 means they strongly disagree with a statement. 5 means they strongly agree with a statement. The y-axis is the number of respondents in percentage. Our feedback was really good. We got no negative feedback. We got some neutral feedback. And we got a lot of positive feedback. The first question, the yellow bar, shows that over 80% give it a perfect score when answering, are these graphs useful? Do you use them? Do they help you with nondeterminism? In conclusion, we present a novel graphical approach to help students understand why non-deterministic finite-state machines reject a given input word. And the novelty here is that we trace the transition diagram and not machine configurations, which is much more natural for students to work with. It's integrated into FSM, a domain-specific language embedded in a racket. For future work, we maybe like to conduct a more in-depth study. We only asked them 5 questions this time around. And maybe add computation graphs to compose Turing machines. We were also playing with the idea of exploring computation graphs that don't require the cutoff threshold. Now, if you're interested in that type of work, we brought up a book about FSM. It's called Programming Based Formal Languages and Automata Theory. Thank you so much.
Thank you, Oliwia. Are there any questions in the room? Yeah. So please speak in the mic.
Really cool talk. I like how you explored the kind of evolution of different ways of visualizing these graphs in the literature. Mm-hmm. I had just a question about your evaluation, which is, I understand you had like 17 students. You you talked about doing a future empirical study. Qualitatively, like, were there any particular insights that you gained from like talking to students in the class? Any things that maybe you like didn't expect from like while you were developing these visualizations, that like feedback you got from individual students maybe?
Sorry. Yes, so of course we talked to students as well. And well, this course has been taught on pencil and paper before this language, right? So what we found out is that students really enjoy creating these machines because, so you implement this machine, it's code, right? And then it usually doesn't run the first time around. And you get these error messages you can debug. And then you create all these pieces of a puzzle to then write this proof, which usually is just kind of annoying for students. But once they have this machine, once they got the feeling for how it works, they actually understand the proof better and don't mind writing it. But with rejected words, it becomes frustrating because once we were able to work with pretty complex machines. At the end of the course, we get into not just regular Turing machines, but Turing machine abstractions, multi-tape Turing machines, composed Turing machines. And they are complicated to debug. So if a word is rejected, it's just kind of reject. No trace, no help. So these computation graphs really did help students because they kind of give you a guide of why this word has been rejected and how to change that. And it really changed their understanding of non-determinism.
Thank you. Another question?
Hey, thank you for the great talk. So I don't know if I understood correctly computation graphs, but it seems that it basically is intersects the diagram with the word that you're checking, right? Mm-hmm. So for sufficiently long words, I imagine it would, just get you the original graph. And I'm just trying to understand what's your experience with, understanding rejection from long enough strings.
Yeah, of course. If it's a word that really traces every path that exists, it's going to be the transition diagram, which is just going to look the exact same way, but now you have these colored states, and it shows you where a computation halts. But it's usually it won't look like that because we also have the dead state. And there's definitely always going to be, well, it doesn't have to be, but it's likely that there's a state where the entire input is not consumed. Here, there's a transition missing that does not read an A, but could. So then it will also have these dashed edges that will let the student also extend this graph. But it's really natural because it's the same transition. Nodes are still states. So it's really easy to associate one with the other. Mm-hmm.
Okay, I think we can only take one more question.
Thank you so much for the talk. I'm wondering if you explored using like animations of the original machine, or allowing like users to kind of step through the state instead of just showing like one static graph. Or do you feel like that's difficult because of like the non-deterministic nature, or like the fact that you can have the machine in like multiple states at once?
Well, it's nice that you asked this question, because it's a good transition to our next talk, actually. So essentially, to answer a little bit more in detail, we have a dynamic tool for accepted words, because there's one computation. So it's just easy. The easiest computation is the one that is the dynamic one. For rejected words, that's not really possible, because there's so many different paths that could be taken. But now we're going to present composting machines with two tools, a static and a dynamic tool, which shows exactly what you just described.
All right.
Thank you.
Thank you very much.